Okay, thank you. They told me to speak about coherent structures, which it was not clear to me why, because this is supposed to be a course on data processing. I'm still going to be speaking about coherent structures, but not only on that. I mean, actually, this is going to be a two-part lecture. Today is the first one, coherent structures in turbulence. Friday is the second one, which is called the computer as a scientist. And the common theme to both lectures is how much can science be automated? Yes? You can't hear me? So there has to be a problem with the loudspeakers, because I can hear the loudspeakers here.
Let's try. I'm increasing. Now is at the maximum.
Can you hear me now? No. No.
It's too much.
Okay.
Right? Maybe now.
Can you make this longer? Okay. Can you hear me now? Okay. Good. Okay. I was saying that the common theme of the two lectures is going to be how much science can be automated. Okay, and the lectures are going to be different. Basically, today I'm going to be speaking about what has happened up to now. So this is going to be a lecture about the past, if you want. And Friday is what could happen in the future. And of course, I don't know what's going to happen in the future. The future is up to us, mostly up to you. But you can see trends. And the basic problem, the basic thing that I want to address, and that's something that you have to decide, is whether you are going to be substituted by a computer. Okay? So this is something that is beginning to become possible. So you have to decide what you want to do. Okay? So, was this a robot PhD student? That's a robot postdoc. I don't have robot PhD students. I have robot postdocs. But, I mean, at some point I wrote a proposal that I finally didn't send that was called "My Postdoc is a Computer." And the postdoc became very offended. Okay, anyway, so let's speak about turbulence, okay? This is going to be this first part is a tale. It's actually going to be a historical tale about structures in turbulence, okay? Structures in turbulence is a funny concept, because you look at something like turbulence, something like this. I mean, this is turbulence in the atmosphere. There are no structures. I mean, turbulence, the fluid mechanics is a continuous field, is a continuous vector field that satisfies a set of partial differential equations. What do I mean by a structure? But then the thing is that, okay, you see that, and this is a mess, so you're going to simplify it. And you have to remember this. The goal is to simplify turbulence in such a way that we can do something with it, okay? And in some cases, you see something that, for example, this thing here, you say this is a cumulus, and you sort of think that the cumulus has an individuality, the cumulus has a history. It has, when there is a cumulus, you know it's going to rain or something like that, okay? So you call this a structure, okay? There are other things that you see in the flow that look like a structure, and they are not a structure, okay? Somehow you feel that might look like a teddy bear or like a dog or something, but this is not a structure. It's something that is going to dissolve in a moment. If it is true, I don't know how fake is that or not. I got that from the internet, okay? And basically, the idea of a structure, at least my idea of a structure, is something that satisfies something like this. There's an evolution equation for the structure. You say the structure is a function of the structure. Okay, the derivative with respect to time of the structure is a function of the structure. And maybe something else, of course. I mean, many other things. But these other things are not important. And here, when you say structure, it might be a few. It might be 3, 2, this cumulus, the cumulus nearby, the cumulus to the left. But not all the cumulus in the world. It's a self-contained thing, okay? But then there is something that you have to understand, that you always have to remember this, okay? This is turbulence. This is the observation of turbulence. This is the equation of turbulence. this idea that the state of the structure in a while is going to be a function of only a few structures is a hope. And you have to, all the time, you have to be going back to see whether your hope is justified or not. Okay? Which, of course, have not stopped people from seeing structures in Turbulent, and this is probably the most famous picture of structures in Turbulent. This is Brown and Roscoe. This experiment, of course, there's no machine learning because basically there were no machines at the time, or almost, okay? And this is a mixing layer. It's a mixing layer is the region. There are two streams. There is a fast stream there. There is a slow stream there. The two streams mix, and in the mixing, there is a turbulent region. Okay, and it was always thought to be a turbulent region. I mean, something with very few information in it. People did statistics about that. But then these guys took a picture, and they saw that there were there was something coherent in there. Okay, and that became very famous, and it became very famous not because it was a picture of coherent structure. There had been pictures of coherent structures before. As you will see later, for wall-bounded flows, things like bounded layers, there were observations that were earlier than that. The reason that this thing became very famous because these structures had been seen before. Okay, and these pictures had been taken a few years before. And this is also a mixing layer, but the Reynolds number is much lower. So this is not turbulent. This is basically laminar. But you still see something that looks very much like that. Okay? So it was known. It was something that you felt that you knew what you were seeing there. And moreover, there was a theory. There was a theory that was not from a few years before. It was already like 100 years old at that time. Okay? This is an instability. I mean, this was well understood that this was an instability. It's called an instability. It has to do, it's called Kelvin-Helmholtz, and Lord Kelvin is in the 19th century. Okay? And it's something that happens when you have a mean velocity profile with an inflection point. It has to do with this inflection point here, a place where the thing goes around. Okay? And this was well understood here, and because when the flow is laminar and the thing is transitioning, this mean velocity profile is there. It was a surprise when they saw it in the turbulent flow, because this mean velocity profile never happens. I mean, there's really never an instantaneous velocity that looks like this, but apparently the flow is happy with that. The flow makes an average over the enough time to have something like an inflection point and something like Kelvin-Helmholtz. Moreover, people were soon able to test this quantitatively. Okay? These people in Israel, basically they had a mixing layer. They force it. Okay? There are several things that are wrong with this Kelvin-Helmholtz model. I mean, the model is linear. We all know that turbulence is non-linear. The mean velocity profile is not there. We all know that the Kelvin-Helmholtz need such like an inflection point. But still, they had a mixing layer. They force it. They have a little flap at the end of the splitter plate, and this thing forced a wave. And they knew how the wave had to propagate according to the linear theory. And then they tested the experiment, which are the symbols against the theory. And it works very well up to a point in which it stops working. And the reason why it stops working here was also understood. They were able to explain why it works up to here and it didn't work up to there. Okay? So it was an observation that came with a theory, and the theory was known and understood. Okay? Moreover, once you have a theory, then you can use it for something. Okay? And this is a use for control. This is a jet. A jet also has an inflection point. The mean velocity profile here looks like this. There is a maximum there. And here, in the two edges of the jet, there are inflection points. Okay? And those inflection points are unstable, like Kelvin-Helmholtz. So that's why you have here these blobs, which are coherent structures. And then, because you understand what is going on, then you can twiggle the jet a little. You can force it, something like this experiment in Israel. And then you got a jet that, instead of looking like this, looks like that. And if you are mixing things, and many jets are dedicated to mixing things, this is good, because you mix a lot more than here. So you have a theory, you have an observation, you have a theory, you have an application that you can do. Okay. Just for the point of view of this course, I just want to mention that this was also one of the first cases in fluid mechanics where big data was used. Okay, and this is something that we did in my group at the time with the group at Caltech. In Caltech, they took a movie, and it was you have to understand at that time it was an analog movie. Okay, there was an analog movie. Okay, but they sent us a movie of the mixing layer, and you have this. You see here the structure, and the structures move. There was an issue. There was a controversy at the time about how these structures grow, because you see here the structures are small, and I don't mean they are small this way. They are small this way also. Okay, and here they have to grow, and they have to become bigger. So somehow they have to merge, or they have to do something to become bigger. And it was not clear how that happened. So what we did is we took the movie, digitized it. Okay, that was 70 megabytes. I mean, 70 megabytes at the time was big data. Well, I mean, you have to realize the standard way of moving data at the time was with floppy disk. The capacity of a floppy disk was 360K. Okay, so this was about this much in floppy disk. Okay, and it really took a big computer, which of course has something like 256K memory or something like that. But okay, but it was still a big computer. Okay, and we were able to automatically find the structures and follow them in time and see what happened, how they merge, how they don't merge. Some of them merge. I mean, some of them do something else. We produce statistics, and everybody was happy with this. And I was reading this paper just to prepare this talk. And then I realized that it was artificial intelligence. I mean, I'll read this paragraph for you. I mean, this is a part in which we are trying to identify these ellipses in there. It says, it is useful to consider these blocks as phonemes in a formal language and descriptive rules as a grammar describing which phonemes can be concatenated to form complex words and which is the meaning of those words. Later, an automaton can be designed to understand the grammar, recognize the words, and blah, 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 blah. Actually, at that time, I was working for IBM, and one of the things that I was supposed to do by my contract is to do artificial intelligence. Okay? Artificial intelligence meant something different then, and I'll make the difference in a moment. But there's also something that I want you to notice in this paragraph. We didn't invent this. I mean, we were quoting textbooks that were even older. Okay, so it was something that these things are very old. It's not something that has happened lately. They have been there for 30 years. Okay, what has been there for 30 years? Okay, well, no, this is the last thing I'm going to say about these free shear flows. Okay, we have an observation. I mean, the end result of this work that took 15 years, but basically half of the fluid mechanics community. I mean, many people work on this, on different aspects of the free shear layer. That was the place to be at the time. Was we got from an observation to something that was really a model of the coherent structures, something that let us do control, something that let us act on the flow. And you always have to remember this. When you do this thing, the purpose is to get something that works. Okay? It's not just artificial intelligence per artificial intelligence. That's basically the hammer syndrome. I mean, if you are a hammer, you go around the world looking for nails. Well, it's either a nail or not a nail. There might be a nail, there might be a screw. And in this case, the point is that you want something, and then you use whatever it takes. In this case, something like artificial intelligence to get it. Okay? Now, let me stop speaking about turbulence for a while and speak about the other part of the lecture. At the end, I told you that this was a lecture about how much of the scientific method can be automated. So let's look a little at the scientific method. The scientific method, science, there are two meanings to the word science. It's either a way to find out things, okay, and there's a method, this is a scientific method, or it is the result of that way, okay? And then we say science. These are the things we know about, blah, 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 okay? This is the acception of science about how to find things out. And it's a very, I think by now it's a very well-organized thing. You make observations. Once you see the observation, you frame hypotheses. Once you have the hypothesis, you test them. If you are happy with the test, then it's finished. Usually you are not. Then you make new observations, make new hypotheses, blah, 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 blah. And this is a cycle in there. I mean, by the way, since we are many, I think that it's better if we postpone discussion until the end. But if somebody gets lost or something, raise your hand and yell, and I will try to do something about it, okay? Basically, okay, so observe, explain, test. Then observe again, explain, test. And depending on who you are, you might start here, you might start there. You might do a hypothesis, and then once you do a hypothesis, you observe and you test it and blah, blah, blah. But this is a general idea, okay? In the case that I told you about the instabilities, the coherent structures in free shear flow, the observation was the thing that were done at Caltech, or the thing that we did in Madrid with their data. The explanation was this Kelvin-Helmholtz model, okay? And this is Kelvin was Iris, I think. And this is Peter Freimouth, which is in Berlin, who was in Berlin, okay? And then you test it, and the test is this experiment with the force layer, or this experiment with the force jet, okay? And in this case, it worked. After a few iterations, it worked. And so people are happy, okay? Now, what about artificial intelligence? I mean, artificial intelligence has something to do with this, but what, okay? And for that, we have to reach an agreement. What do you mean about artificial intelligence? You talk to the people who do artificial intelligence, the theorists of artificial intelligence, the computer people, okay? They tell you, okay, I mean, you mean symbolic or sub-symbolic? Okay. I mean something, okay? Well, no, I mean, there's a big difference, okay? The intelligence that you can usually think of is what is called symbolic intelligence, okay? Including symbolic artificial intelligence. Basically, you have a hypothesis, you have an idea, and you create rules, okay? I tell you, okay, well, I'm looking for structures, and I look at it, and they look like ellipses. I'm going to find ways to find those ellipses, and then see how the ellipses work, okay? So you get from my hypothesis, you create rules. And this is the classical thing. This is what I was doing in 1980s, okay? This is what people were doing in 1970s, I mean, when I was still a student, okay? It uses theories and it tests theories, okay? This is what is going on here. And this is mostly human, okay? This is the whole idea that artificial intelligence has to mimic the way that people think, okay? The other route is what was described this morning by Bern. This is what is called sub-symbolic intelligence. There are no rules here. I mean, you don't care about rules. I mean, you don't even want to know what is a coherent structure. You just want to do something with them, okay? So you start with a map. This is the measure turbulence, and I have assumed that in this case I want to identify vortices, so I somehow decide, tell the machine this is a vortex, this is a vortex, this is a vortex, this is not a vortex, blah, 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 blah. And then launch the self-organizing map on this, and at the end it gets some rule. I don't know exactly what the rule is. It might not even be a rule. It might be a set of, when there is a pixel to the right and a pixel to the left that have nothing to do with fluid mechanics. But when I give them a new piece of the flow, it tells me this is a vortex or not, okay? Now, this thing, the problem with sub-symbolic intelligence, it produces no theory. Once you are done with it, you don't know what is going on. I mean, you know nothing about the flow. You know nothing new about the flow. And there is a question, and it's a question that we have to think, and this is what I want you to think with me for these two talks, is whether this is scientifically useful. Okay, this is something that I will speak more on Friday, but please think on it. I mean, is it something that you want to do or not? Okay, because there is a real. I mean, I want to insist on that. There is a real chance that many of the things that we do as scientists or as engineers will be outsourced to computers. And then we'll have to do something else, which we might enjoy or not. Okay. So let's move to the other example of turbulence, which is the thing that I have been working for the last 20 years, maybe, which is not free shear turbulence. It's not something like a free shear layer. It's turbulence with walls, boundary layers, pipes. Okay, these things are technologically very important. Actually, you can look in web pages and estimate how much energy goes into what. 5% of the energy that is being spent, I wouldn't say wasted, but spent in the world to do something, is spent in wall friction. Okay, and that's a lot. That means 1 every 20 tons of CO2 goes into wall friction. So anything that we can do about it might be useful. Okay. Now, are there structures in there? Can we use structures to simplify our understanding of what happens near the wall? Well, this is I mean, as I told you, this is something that was observed before even Brown and Roscoe made their pictures of the free shear layers. These guys, Klein, Kim, and a bunch of people at Stanford, they made a picture of a boundary layer. Here you're looking into the wall. There's a flow coming from the left to the right, and they put some tracers in some places near the wall, and the places organize themselves into these streamers that they call streaks. Okay. Now these people were really amazing. I mean, I have seen some of the original movies that they used for that. I cannot see anything. I mean, but they really got a lot of understanding out of looking at this. I don't know what you want to call this big data. I don't even know whether this thing was ever measured in kilobytes. These were analog pictures, okay? But if you can think of how much information is in those pictures, it's like of the order of 100K or something like that, okay? And they still saw the streaks. They saw that the streaks sometimes broke down, and there seemed to be fluid coming from the wall up, and they called this an ejection. There were places where the fluid seems to be going from the top down, and they called that a sweep. And they basically started the nomenclature of this. Okay, understanding a little more about this had to wait for the computer, and the computers came like 20 years later in the 1980s. Okay, the first computer simulation of something like this were the computations in a channel of Kim, Moyne, and Moser. Okay, and the first the first catalog of the things that were in there was done by Steve Robinson a little later, who took a movie of this. Okay, and this movie of this is about 30 gig, which was, by the time, it was very big. He had to do this in a cray, one of these big crays at NASA Ames. Okay. And basically he did it by eye. I mean, he sat in front of the screen for 6 months and cataloged what was in there, and decided, okay, well, there are the streaks, and the streaks turn out to be velocity features, okay? Stream-wide velocity features. There are some places where the flow goes faster and some places where the flow is slower. These are these gray things in there. And the sweeps and ejections are the two sides of vortices, which are these color guys in there. The sweeps, the vortex is going like this. There's an ejection, a sweep here, and an ejection there. Okay, and these sweeps and ejections are the things which are churning the flow around, and they're at the end they're creating the streaks. And the point then became how to understand what was going on. I mean, how the two things were connected to each other. Then time passed. The computers got bigger, and essentially by now we know everything about these structures. Okay, this is something like this, but now the Reynolds number is much bigger. The amount of data is also much bigger. This is now roughly state of the art. You work with data sets which are of the order of 500 tera, maybe 1 peta if you are very big or something like that. But then we know everything about this. I mean, or not. Okay? I mean, you know, something that you have to always, I mean, I told you at the beginning, you always have to be careful to make sure that what you are doing makes sense, okay? Because the structures don't exist, they are your construct. And you have to keep going back to make sure that your construct has something to do with the flow.